Hi, everyone. It's an absolute honor to be here speaking at Rails World 2025. Infrastructure is a top priority at Shopify, and I am sure it is at your company as well. It is important to prevent outages, to prevent data corruption, and ultimately to have a good user experience. In this talk, I'll be covering some ways to prevent and respond to instability in Ruby. You can find the slides at this URL or by scanning this QR code. Don't worry if you end up missing this, because I'll also have this QR code up at the end of this talk. So first, I'll talk a little bit about me. That's what I look like on the internet. I'm currently based in Toronto, Canada. I'm on the Ruby core team, and I'm a staff developer at Shopify on the Ruby infrastructure team, where I work on performance and memory management in Ruby. I'm the co-author of the variable width allocation feature in Ruby, which improves performance and memory efficiency of Ruby's garbage collector. I'm also the co-author of the Ruby free at exit feature, which frees memory at shutdown to allow the use of memory leak checkers such as Valgrind or the macOS leaks tool. I also designed and implemented the modular garbage collector feature in Ruby. I'm also the author of the Ruby memcheck and the autotuner gems. And in my free time, I like to travel and take photos. And I post them on Instagram at peterzhu.photos. So first, I'll talk a little bit about the outline of this talk. We'll first take a look at what the infrastructure of a typical Rails app looks like, the teams that you might have maintaining this, and where you might have blind spots in your infrastructure. We'll then take a look at some of the ways Ruby could cause instability in your infrastructure, and ways to proactively prevent crashes from happening in production. We'll end off by discussing how to capture metrics and information about crashes, and how we can use that information to debug. There are many moving parts and many layers to the tech stack of a Rails app. In your company, you might have teams dedicated to each part of this stack. And let's see a simplified example of a typical Rails app. And here's a diagram of a simplified example of what your infrastructure might look like. You might have teams that manage external services, such as a database, your caches, or other microservices that you use. You might have teams that manage deployments of your app in production using tools like Docker and Kubernetes. You probably have a large number of product developers working on your Rails application. You might have some product developers that might be Rails experts, or you may even have whole teams dedicated to the architecture of your app. And these people would be responsible for reducing tech debt, for triaging and debugging exceptions that happen in production, and performing upgrades for Rails and gems and Ruby. However, all of this runs on top of Ruby. And Ruby is just another piece of software. So it can have bugs, and it can crash. Do you have people responsible for maintaining this level in your tech stack? Do you have observability into this layer? And do you know what to do when Ruby crashes? In this talk, I'll be talking about some of the reasons why Ruby could crash, how to get information and metrics about these crashes, and what we can do about it. So let's first take a look at why Ruby could crash. Or, I should add, and native gems. Your app may have tens or even hundreds of native gems. And in fact, if you don't believe me that there's a lot of native gems in your app, a brand new Rails app installs 21 native gems. This adds 21 additional possible sources of instability inside of your app. And so now let's take a look at some of the common categories of bugs that Ruby and native gems run into. Ruby is written in C. And so are a lot of native gems. This means that they can run into bugs found in C code. So in C, you have to manually allocate and free memory. This is unlike Ruby, where we have a garbage collector which determines when an object is alive or dead. So if you free a piece of memory in C before all of the places give up references to that piece of memory, then you could cause a lot of different problems, including crashes or unexpected behaviors. And this is known as a use after free bug. Let's see a quick example. This is a short snippet of C code. And we first allocate memory using malloc, and we write the string hello Rails world into it. Then we print out the string. And then we free the memory holding that contains the string. And then we print the string again. This is not allowed, and because this is a use after free bug, and the behavior of that is non-deterministic. It could either crash, or it could even read other pieces of memory. There are also buffer overflow bugs which access past the end of a region of memory, which could potentially cause a crash. Or it could even potentially end up reading another piece of memory. And so this could open up your app to attacks and allow attackers to read from or write to other pieces of memory. The attacker could exploit it to perform unintended behaviors in your app, or even brute force it to read other pieces of memory, such as users' passwords or secrets in your infrastructure. Let's see a quick example. This is the program again. It's similar to the example that I've shown for the use after free bug. But what's the difference? Do you see where the bug is? You're missing the +1 for the null terminator when we malloc. The null terminator is important because it signals that it is at the end of the string. And so the stir copy here, which copies into that string, will now write the null terminator past the end of the region of memory that was allocated. So it could be it could be writing into another piece of memory. And the printf after it will now read past the end of that region of memory. So if that null terminator was overridden by someone else, then this would allow the attacker to read that region of memory. So here's an example of an error that we saw in our production system. Our developers saw this in production, and you might be wondering, what is course ID? It looks like a typo, doesn't it? If we look at the stack trace, it's erroring out on this line of code. And that doesn't make any sense, because the code clearly says source ID, not course ID. So what happened to the first character of that symbol? If we look at the ASCII table, lowercase s has decimal 73, and in binary it looks like this. Lowercase q has decimal 71, and it looks like this in binary. Notice how the two characters differ by 1 bit. So somewhere, someone has flipped the second bit of this character. The cause of this bug was not certain, but it was possibly a use after free or buffer overflow bug where someone wrote to memory that it no longer owned. C requires manual memory management, so if you forget to free that memory, then it will leak. A few of these memory leaks are benign. Ruby might end up just using a little bit more memory. However, if it keeps on happening, then the Ruby process will eventually run out of memory and be killed by the system. This could cause instability in your system, as the Ruby process may be terminated by the system halfway during a request. At Ruby Kaigi 2024, I gave a talk with Adam Hess from GitHub about finding and fixing memory leaks in Ruby and in native gems. If you're a native gem maintainer, you can take advantage of the Ruby free at exit feature and the Ruby memcheck tool that I built to find memory leaks in your native gem. Ruby C API can run into bugs that we don't encounter in Ruby code. This is because Ruby has automatic memory management via the garbage collector, whereas C has manual memory management. And this difference in memory management paradigms means that we need to be aware of how the Ruby garbage collector works when we are writing C code. The most common type of bugs are missing garbage collector guards. When Ruby runs the garbage collector, it scans the C stack to find potential Ruby objects in order to keep them alive. This is known as conservative stack scanning. However, the C compiler may optimize the stack space and reuse local variables on the stack. And these local variables may contain pointers to objects that are actively being used. And this would cause objects to be recycled or moved by the garbage collector, causing unexpected behaviors in our code or even crashes. So to demonstrate missing GC guards, let's implement this simple Ruby method called array each byte using the C API. It calls this block with the integer value of each character in each of the strings in the array. And we can see an example here of how to use this method and the output that it generates. So this is the C implementation of the method. It's missing some checks, like checking that each of the elements in the array is actually a string, but that's not really important for this demonstration. So let's quickly take a look at this implementation. So we first run a for loop that iterates a counter over each element in the array. We then get the string object at that particular index. And then we get the underlying character buffer of the string and the length. We then iterate a counter over each character in the string, and then we yield the character in the string by converting it to a Ruby fixed num. So now let's try running the same script, but running this method called verify compaction references, which manually runs garbage collection compaction in the block. Normally, compaction tries to be efficient by minimizing the number of objects moved in the garbage collector. However, since we want bugs to show up, this method will allow us to move the maximal number of objects possible. So then, if we try to run this, we see incorrect output. And sometimes when we run it, it even crashes. So clearly, something isn't right here. And if we look at the code again, what we're missing is a GC guard. And we need a GC guard right at this line. Because the str variable here isn't used later on in the code, it's optimized out of the stack by the C compiler. However, this makes it invisible to the Ruby garbage collector that we're actively using this object in the for loop where we're yielding each character of the string. So the string object ends up getting moved. And so by adding this GC guard here, it ensures that the C compiler will keep the variable alive on the stack up until that point. So now we can run the script again, and we will see correct output. So error raised in Ruby interrupt your normal flow of your program. And it could jump multiple stack frames in Ruby. And it behaves similarly in C. And it uses a C feature called long jump in order to skip stack frames. However, if you have manual managed memory, it could be lost and leaked when you do that long jump. So we need to be careful in determining what code could raise errors when we're writing C code for native gems. Missing write barriers could also cause subtle bugs. And write barriers are hard to implement correctly. They are a little bit difficult to explain. So learning more about this is left as an exercise for you, the viewer. As a side note, there is a common misconception that people have. And this misconception is causing an increase in instability in our systems. And I'm talking about the rise in the number of Rust gems, mainly due to the popularity of Rust and the promise of memory safety from the borrow checker in Rust. While this is true, many Rust gems directly interface with the Ruby C API. Ruby has a C API, not a Rust API. So there are many implementation challenges for Rust gems, including how to get Rust to work properly with the Ruby garbage collector. Additionally, Rust gives developers a false sense of security, so many developers don't truly understand the code that they've written. So as a recap, this section was about some common bugs in Ruby and in native gems. We looked at bugs in C code, including use after free buffer overflow and memory leaks. We also looked at some incorrect uses of the Ruby C API, including missing GC guards, raising errors, causing memory leaks, and missing write barriers. Now let's look at some ways to catch and prevent bugs before they reach your production systems. Ruby has powerful ways to check its internal state and run in more extreme ways for bugs to reproduce sooner. So now let's take a look at a few of these. Ruby has assertions in the code to check that Ruby is running correctly, and that the assumptions we make during runtime in the Ruby VM are correct. These assertions are turned off by default because of the negative performance impacts that they bring. However, it is useful to run with these assertions turned on in CI because it can catch bugs in Ruby and in native gems before it is deployed to production. In order to enable assertions, we have to compile Ruby differently by adding this Ruby debug to the CPP flags during the configuration step when we compile Ruby. So for Ruby build that ships with RBenv, you want to use the configure ops environment variable. And for Ruby install that ships with Cherubi, add the CPP flags using a double dash at the end of the command. Compiling Ruby with assertions enabled is documented in the official Ruby contributing guides. Since Rails 7.2, all apps enable the YJIT just-in-time compiler by default, which improves performance. However, a just-in-time compiler performs optimizations and compiles Ruby code into machine code, so it is yet another additional source of bugs. YJIT by default only compiles the hot code, meaning code that is the most commonly ran. And because compiling code has performance and memory impacts, YJIT limits it to code that is executed the most frequently. However, this may mean that not much of the code in tests are using YJIT because code in tests aren't executed repeatedly. So by setting the YJIT call threshold to 1, YJIT will compile the code the first time it executes it. C uses manual memory management. We've learned about that. So it is not uncommon to have memory errors such as use after free or out-of-bounds memory access. Malloc implementations are designed to be resilient against memory errors in order to prevent memory attacks. However, if there is a memory error in your app, then resiliency is exactly what we don't need during testing. So there are tools that can help us find memory errors, such as Valgrind or Address Sanitizer, also known as ASAN. Here's an example of a memory error in ASAN. When it encounters a memory error, it causes the program to crash and output an error message that looks like this. These tools are powerful because they do extensive checks on every memory access. Therefore, they make your program run several times slower and use much more memory. So you'll need to keep that in mind and adjust timeouts and memory limits in CI in order to accommodate these tools. So for more details on how to build Ruby with ASAN, follow this guide in the official Ruby building guides. We also run nightly tests on our Rails monolith against the latest commit of Ruby's master branch. This helps us accomplish two things. First, it allows us to find incompatibilities in our code base with the next version of Ruby. This helps us incrementally discover these incompatibilities instead of having to do a big push for Ruby upgrades each year. Secondly, it allows us to discover bugs in Ruby that was not caught by Ruby's test suite. We run our nightly CI against Ruby head with various configurations mentioned before, like enabling assertions, running with YJIT call threshold of 1, and with ASAN enabled. This has helped us find a wide variety of bugs in Ruby in native gems and makes our annual Ruby upgrade easy. For these reasons, I encourage your company to also run nightly CI against Ruby head across various configurations. And then when you run into crashes or regressions in Ruby or native gems, or any gems, open bug reports and send fixes upstream. So to recap, in this section, I talked about some techniques to prevent crashes in production. First, I talked about compiling a Ruby with assertions enabled, which checks the internal state of Ruby. And second, running with YJIT call threshold of 1, which makes YJIT compile every method that gets ran. And lastly, using a memory checking tool such as Valgrind or ASAN. So there's still the inevitable case where bugs are not caught by CI and only happen in production. So now let's see how we can capture information about crashes that happen in production. When Ruby crashes, it generates a crash report that includes what kind of crash it is, the Ruby stack trace, and the C stack trace. Here's what a crash report looks like. We can first see what kind of, I went a little too fast. We can first see what kind of crash this is, and this one is a segmentation fault, meaning that it is some sort of memory error. We then see the Ruby stack trace, and using this information, we can try to isolate the issue and even try to find a small reproduction script for this crash. We can then see the C stack trace, and this is useful for determining where the bug comes from, whether it's a bug in Ruby or in a native gem. And we can also use this to look at the source code in Ruby or in native gems. And just by looking at the source code, sometimes we may be even able to just identify the bug. So normally, this crash report outputs to standard error. However, as of Ruby 3.3, you can also redirect this crash log into a file. The Ruby crash report environment variable is documented in the Ruby man pages and explains how to add specifiers to the file name for timestamps or the process ID in the generated crash log. So the crash report is often not enough to debug crashes. We need to capture core dumps from the crash. But what are core dumps? Core dumps are files generated containing the state of the program at the time of the crash. This includes everything on the C stack and heap, and includes all local and global variables. And then we can open up this core dump in the debugger and try to find the bug. However, core dumps only contain the state of your program at the time of the crash. So it may be hard to determine how you ended up in that state. And one thing to keep in mind, though, is that core dumps contain all of your program's memory. And this includes things like decrypted user passwords and PII in plain text, as well as your infrastructure secrets. So make sure to treat core dumps with great care. At Shopify, we upload core dumps to the cloud so we can debug them. But we make sure the access to the cloud bucket is restricted to specific teams. And it is encrypted in order to protect against attackers who gain access to that bucket in the cloud. At Shopify, we use a closed source tool called Crash Reporter to upload core dumps that we generate in production. This tool essentially does three things. It first uploads our core dump to the bucket in the cloud. Then it detects if the crashing binary is Ruby. And if it is, then it finds the associated crash report that we've written to disk and uploads it. And then finally, it creates an event in our error monitoring system in order to keep track of this crash. So the first step is capturing the core dump when it occurs. So you can configure the behavior in Linux when a program crashes. By default, it does nothing. You can also configure it to write to a particular file, or you can also use this feature, which is the one that we use, that pipes the core dump to a program's standard input. So our crash reporter tool reads this core dump from the standard input and uploads it to a bucket in the cloud. Then secondly, when we have the core dump, we detect whether this core dump is from Ruby. And if it is, we try to find the associated crash report and upload it because it contains valuable information such as the Ruby and C-level stack traces. Finally, we keep track of these crashes by creating an event in our error monitoring system. We also, at this step, parse the crash report acquired in the previous step for the Ruby and the C-level stack traces. This information is useful for quickly triaging crashes and determining if this crash is a new or a known issue. And using the Ruby level stack trace, we can even use it to try to find a minimum reproduction of the bug. So now that we've collected the necessary information for the crash, we need to use it to figure out what the bug is. Here's an AI-generated image of what that process looks like. And I'm going to be honest, I could spend hours here giving tips and techniques. But there are so many possibilities that even during that time, I couldn't even possibly cover all of the potential issues. We've even seen cases where the C compiler we used to compile the Ruby binary and native gem had a bug in it, and it was emitting incorrect instructions into the binary. But I'll briefly talk about how to debug core dumps generated from production. So in order to debug core dumps, we need the following things. So of course, we'll need the core dump file. We'll need the original binaries of Ruby, system libraries, and native gems. And we need these because they contain the symbols in order to output meaningful stack traces, structure definitions, and variables. And we need to be on the same operating system and usually the same CPU architecture as the production system. Those are quite a few requirements, but fortunately, if you're using a container system like Docker in production, you can instead just use the production container to debug the core dump. So in order to debug the core dump, you open the core dump up in a debugger, such as GDB or LLDB. You need to specify what the core dump file is and the Ruby binary that was crashing. Then when you're in the debugger, you can analyze the core dump by looking at the backtrace and read variables and pieces of memory. So to recap, in this section, we talked about some ways to capture information about crashes. We saw what a crash report looks like and how to redirect crash reports to a file in order to capture it. We looked at what core dumps are and how we can generate them on Linux systems. Finally, we looked at how we can open core dumps in a debugger in order to debug it. So once you've found a bug, you should report it. If it's a bug in a native gem, let the maintainer know. If it's in Ruby, let us, the Ruby core team, know about it by reporting it to the bug tracker. But wait, before you open a ticket, is the Ruby you're using an actively maintained version of Ruby? If you're unsure, consult this page. Right now, only Ruby 3.3 and 3.4 are in normal maintenance mode. And Ruby 3.2 is only in security maintenance, meaning that regular bugs are no longer fixed. So if you're running on Ruby 3.2 or earlier and there are crashes, then try upgrading your Ruby version first. Additionally, make sure you're running on the latest patch version of your major version of Ruby. These contains all of the backported fixes, and the most recent version as of this talk is listed here. If you're running a maintained version of Ruby and you're on the latest patch version, then submit a bug report on the Ruby bug tracker, and maybe even try to submit a fix. The guide linked here explains how to report bugs on the bug tracker, including what kinds of information to include in your ticket. At Shopify, when we fix a bug in Ruby, we want to upgrade our Ruby version to include that patch as soon as possible. However, a new version of Ruby may not come out for a few months, so we create an internal release with these fixes backported. We've made all of our Ruby definitions public, and you can find it in the Shopify/Ruby definitions repository. This contains Ruby build definitions for all of the custom Ruby versions we run at Shopify. So today, I've covered quite a few topics, including why stability of Ruby is important, some sources of instability in Ruby, how we can catch bugs in Ruby and in native gems before they reach your production systems, and finally, how to debug core dumps that you've captured from production. So you can find a copy of these slides at this QR code. If you have any questions, feel free to ask me after this talk, or through social media, or through email. Thank you for coming to my talk.